anyone finds this, we didn't know the reservoir was there. We just wanted to give Mars an atmosphere. We punched the crust and it punched back.
That was my father, Dr. David Ward. He died on August 3rd, 2022 at 9:30 UTC, trying to force a dead planet to breathe. He was 34 years old. I wasn't born yet. My mother was 4 months pregnant on Luna, waiting for his rotation to end. He never came home. This is the story of the most arrogant thing humanity ever attempted. We didn't just colonize Mars. We decided to rebuild it, atom by atom, molecule by molecule, against every law of physics that said it was impossible. My name is Marcus Ward, grandson of Elias Ward, who helped build the city of New Eden, son of David Ward, who died in the Hellas Impact steam eruption. I'm 85 years old. I was born in the year 2310 in the city of New Eden, 70 meters beneath the Martian surface, in a rotating habitat ring where artificial gravity pressed my infant bones into something approximating human strength. I've spent 7 decades working on atmospheric systems, trying to finish what my grandfather started and honor what my father died for. And I'm still not sure if we saved this world or just killed it slowly in a different way. What you're about to hear spans 3 centuries, 4 voices, hundreds of deaths, thousands of impossible choices, and one question that still keeps me awake at night. Did we have the right to change Mars? Or did Mars have the right to stay itself? By the end of this story, you'll know how we turned a frozen red desert into a world with blue skies and rain. You'll know the names of the people who died making it happen. You'll know the science, real science, not fantasy, that made it possible. And you'll have to answer that question for yourself. Because the road we're on, the road to becoming a civilization that spans the solar system, it doesn't end with Mars. It continues to the asteroids, to Jupiter's moons, to Saturn, to the stars beyond. If you want to see where that road leads, subscribe to Vivid Futures now, because this is just the beginning of the Solarian Chronicle, the story of how humanity learned to live beyond Earth, and what it cost us to get there. Now let me take you back to the year 2200, when Mars was still red. When the atmosphere was so thin you could see stars at noon. When we looked up at that pink sky and dared to imagine it blue. By the year 2200, humanity had lived on Mars for over a century. We had buried cities in lava tubes, built spinning wheels that gave us Earth-normal gravity, constructed hydroponic farms that could feed tens of thousands. We had fusion reactors humming beneath the regolith and supply chains stretching back to the moon, to Earth, to the asteroid belt. But we were still visitors. Every breath was manufactured. Every drop of water was recycled until it tasted more of machinery than moisture. Every hour spent on the surface was a countdown. How long until your radiation dosimeter started screaming? How long until a pressure seal failed? How long until Mars reminded you that it didn't want you here? My grandfather, Elias Ward, had been one of the early settlers. He came from Earth in 2028-7, worked on the infrastructure that kept New Eden alive, watched friends die when equipment failed or bad luck struck. He kept journals, physical journals, handwritten on actual paper, which was expensive as hell on Mars, but he said typing didn't have the same weight. I have those journals now. 73 volumes. The last entry was written 3 days before he died in the year 2387, at age 61 from complications related to radiation exposure he'd taken during a solar storm in 2352. He never got to see the sky turn blue. He died breathing recycled air in a hospital bed in New Eden, surrounded by machines, asking my father, his son, David, whether the Green Mars Project would respect what Mars was before we decided what it should become. My father didn't know how to answer him. Neither did I when my turn came. The dream, the impossible, necessary dream, was to make Mars breathe on its own, to make the sky blue, to make rain fall without human intervention, to walk outside and live. But there was a fundamental problem, one that killed the original Martian atmosphere 4 billion years ago. Mars is a corpse. It died when its magnetic field collapsed, and the solar wind, a continuous hurricane of charged particles streaming from the sun at 400 kilometers per second, began ripping away its atmosphere, molecule by molecule, year by year, eon by eon. Let me put this in perspective. Right now, at this moment, Mars loses about 100 grams of atmosphere per second to solar wind stripping. That doesn't sound like much, but over 1 billion years, over 4 billion years, it adds up. The Mars we inherited in 2020 had an atmospheric pressure of 600 pascals, less than 1% of Earth's. The air that remained was 95% carbon dioxide, utterly unbreathable, and so thin that liquid water couldn't exist on the surface. It would sublime directly from ice to vapor. NASA's MAVEN spacecraft, launched back in 2013, measured this atmospheric loss in real time. The studies are clear. Without a magnetic field, Mars cannot hold on to a thick atmosphere for geological timescales. The solar wind strips it away faster than volcanic outgassing can replace it. If we were going to thicken the atmosphere, if we were going to pump in greenhouse gases, melt the ice caps, release trapped carbon dioxide from the regolith, we first had to stop the bleeding. We had to give Mars back its magnetic shield.
Ladies and gentlemen, what we're proposing is simple in concept, staggering in execution. We place a superconducting electromagnetic coil at the Mars-Sun L1 Lagrange point, approximately 320,000 kilometers sunward of Mars, and generate an artificial magnetic dipole field with an induction strength of 1 to 2 Tesla. This field would create a magnetotail, an elongated magnetic bubble, that would envelop Mars's day side. The solar wind would be deflected around this bubble, just as Earth's magnetosphere deflects it today. Mars would sit in the lee of our artificial shield, protected.
The chief architect of this insane, beautiful idea was Dr. Robert-Mbara, a Kenyan-American physicist born in Nairobi in 2138. Educated at MIT, he spent 30 years designing magnetic confinement systems for fusion reactors on Luna. He understood superconductors the way musicians understand instruments. He could make electricity sing. He was 62 years old when the Artemis Consortium, a partnership between M-Corp, Prometheus Systems, NASA, and the Sol Accord, approved funding for what would become the largest single structure humanity had ever built in space. Dr. Mbara's plan for an artificial magnetosphere isn't science fiction. It is based on actual NASA research. Back in 2017, NASA's Planetary Science Division held a workshop where Dr. Jim Green and his team proposed exactly this concept. They ran simulations showing that an L1 magnetic dipole, about 320 Mars radii away, could stop the solar wind stripping. They knew the math worked. The studies are published. The physics works. They just lacked the materials and resources. It took the AGI-driven discovery of vanadium-gallium superconductors to finally build the loop that NASA dreamed of 200 years earlier. The L1 artificial magnetosphere, officially named the Ward-Mbara Shield after my grandfather helped with the initial logistics planning before he died, took 7 years to build. The superconducting material was a vanadium-gallium alloy, manufactured in zero-gravity foundries in orbit around Luna, capable of carrying 16,000 amperes of current without resistance once cooled to near absolute zero. Robots and human crews working in the void between worlds, assembling the coil segment by segment, testing current flows, calibrating magnetic geometries. The engineering tolerances were absurd. Any flaw in the superconductor, any microscopic impurity, any stress fracture, and the system would quench. The superconductor would suddenly become resistive, the current would generate heat, and the heat would propagate in a catastrophic thermal runaway, melting the entire structure from the inside out. It had to be perfect. There was no room for good enough. I was 8 years old when they finished construction in 2027. I remember watching the activation ceremony on the screens in our school's common room in New Eden. Every kid on Mars was there. Every person on Mars, on Luna, in orbit, back on Earth, everyone was watching. Dr. Mbara was at the L1 station itself, a small crew habitat attached to the coil structure. He spoke to us from 320,000 kilometers away, his voice carrying an 8-second time delay because of the speed of light.
To everyone watching from Mars, from Earth, from across our solar system, today we take the first step in healing a world. 4 billion years ago, Mars lost its magnetic field and began to die. Today, we give it back, activating primary current feed. Current rising, 1,000 amperes, 5,000, 10,000, 14,000 amperes, 16,000, current steady. Magnetic field strength, 1.8 Tesla. Field geometry stable. Mars, you are now within the magnetotail.
Telemetry from surface stations confirms atmospheric loss rates have dropped by 40% instantaneously. The shield is holding. We celebrated that day. We thought we'd won. We thought the hard part was over. We were so goddamn naive. 3 months later, the sun tried to kill us all. On June 8th, 2208, at 9:17 Universal Time, the sun ejected a coronal mass ejection, a CME, directly toward Mars. This wasn't a small event. This was a Carrington-class storm, one of the largest solar eruptions of the 23rd century. The plasma cloud was traveling at 2,000 kilometers per second. It would reach Mars in 32 hours. Ellen Torres, director of Mars operations at the time, a woman who'd spent 20 years managing crisis after crisis, called an emergency meeting.
People, this is the big one. The Ward-Mbara Shield was designed to handle normal solar wind. This isn't normal. This is a freight train. If the shield fails, we're looking at radiation levels high enough to fry electronics, spike cancer rates, and potentially cause acute radiation sickness in anyone on the surface.
Dr. Mbara was still at the L1 station with a crew of 4. 44-year-old American systems engineer James Brown, 38-year-old Japanese-American physicist Sandra Yamamoto, 51-year-old Russian power system specialist Dmitry Volkov, and 29-year-old Mexican-American structural analyst Carlos Mendez. They were the only humans within 300,000 kilometers of the shield. They were alone. The plasma cloud hit the shield at 6:47 UTC on June 10th. Later analysis showed the magnetic pressure on the field was equivalent to 200 years of normal solar wind compressed into 6 hours. The shield held. Barely. But the current overload was catastrophic.
Mars Control, this is L1 station. We have multiple superconductor quenches. Segments 7, 11, and 15 are offline. Thermal runaway, current interrupted. The magnetic loop is incomplete. We're hemorrhaging field strength on the northern quadrant.
L1, we copy. Surface stations are reporting radiation flux climbing. Agricultural Dome 3 in New Eden just triggered evacuation protocols. Bob, can you restore those segments?
Negative. The superconductors have quenched catastrophically. They're resistive now, generating heat. We'd need to physically replace them, and we don't have spares up here. It would take days to fabricate new ones. But I can reroute. If I bypass the damaged coils and increase current in the remaining functional segments, I can close the magnetic gap. It'll overstress the working coils. We'll be running at 22,000 amperes instead of 16,000. But it'll hold the field geometry until the storm passes.
Bob, how much overstress are we talking about?
Enough that if anything else fails during the reroute, the whole grid could cascade. We'd lose the entire shield. But if I don't do this, New Eden is going to absorb 400 millisieverts of radiation over the next 6 hours. Children in those surface domes are going to get acute radiation sickness. Helen, people will die.
Do it!
Confirmed.
Rerouting now, bypassing segments 7, 11, 15, redistributing current to segments 1 through 6, 8 through 10, 12 through 14, and 16 through 20. Current rising, 18,000 amperes, 20,000, 22,000. Magnetic field strength recovering. Northern quadrant gap closing. Geometry stabilizing. Mars Control, you should see radiation flux dropping in 3, 2, 1.
Radiation levels falling across all stations.
Surface flux back to tolerable range. Bob, you did it.
The rerouted current worked. The shield held. New Eden was saved. Agricultural Dome 3's evacuation was called off. 0 casualties on the surface. But the 22,000 ampere current surge through the functioning coils generated an electromagnetic pulse inside the station itself. The EMP fried the electronics controlling the station's radiation shielding, the lead-lined panels that were supposed to protect the crew from solar particle radiation and X-rays. Dr. Mbara and his team were exposed to 8 sieverts of ionizing radiation over the next 2 hours before rescue ships from Mars could reach them and evacuate them to shielded medical bays. 8 sieverts is a death sentence. Not fast, slow. The kind of death that takes weeks and steals dignity piece by piece. Acute radiation syndrome, bone marrow failure, immune system collapse, organs shutting down one by one. All 5 of them died within 6 weeks. Dr. Robert Mbara, James Brown, Sandra Yamamoto, Dmitry Volkov, Carlos Mendez. They saved 50,000 people on Mars. They paid for it with everything. At the memorial service, Dr. Mbara's daughter, Amara, read from a letter her father had written 2 days before the storm. He'd written it to his grandchildren, kids who would grow up on a Mars his sacrifice had helped protect. The Ward-Mbara Shield still operates today. It's been upgraded 17 times. It's weathered 103 major solar storms since that first one. And every engineer who works on it learns Dr. Robert Mbara's name on their first day. But protecting the atmosphere was only step 1. Now we had to build it. We had to warm a frozen planet. We had to make Mars want to hold on to the gases we were about to give it. That's when the real fights began. In 2205, a third-generation Martian engineer named Dr. Yuki Tanaka, born in New Eden in 2017, MIT-trained materials scientist, chronic insomniac, the kind of person who solved complex problems by talking to himself out loud at 3 a.m., proposed something that sounded completely insane. He wanted to dust Mars with glitter. Not metaphorical glitter, not poetic language. Actual, engineered particles. Aluminum and iron nanorods, each one 9 micrometers long, about 1/10 the width of a human hair, designed to float in the upper Martian atmosphere and trap heat like microscopic greenhouse mirrors. The science was elegant. Mars's problem wasn't just that it was cold, average surface temperature -60 Celsius. It was that the thin atmosphere couldn't trap heat. Sunlight hit the ground, warmed it, but the infrared radiation just escaped back into space. No greenhouse effect, no thermal blanket. Traditional solutions involved pumping greenhouse gases into the air, CFCs, perfluorocarbons, methane. But those gases require massive industrial production. They're chemically complex, and they degrade over time, requiring constant replenishment. Yuki's nanorods were different. They were made from Martian regolith, the dust and rocks already on the surface. Crush the regolith, extract aluminum and iron through electrolysis powered by our fusion reactors, extrude them into precisely shaped rods, and release them into the upper atmosphere where they'd stay aloft for months, suspended by Martian winds. This isn't speculation. This is based on a 2024 study from the University of Chicago, actual peer-reviewed research published in Science Advances. The study, led by Samina Ansari and colleagues, showed that engineered nanoparticles made from Martian materials, specifically 9 micrometers long, could warm Mars by over 50 degrees Fahrenheit with continuous injection rates of just 30 liters per second. The particles would be 5,000 times more efficient at trapping heat than traditional greenhouse gases. The physics relied on the optical depth principle. The rods let sunlight in, but blocked thermal infrared from escaping. We were literally using 21st century theory to warm a 23rd century world. Simulations showed that with continuous injection, you could raise Mars's temperature by 30 degrees Celsius within decades, not centuries. That's the difference between frozen CO2 staying locked in the poles and beginning to sublime into the atmosphere, kickstarting a greenhouse feedback loop. But efficiency in a simulation doesn't mean feasibility at planetary scale. To warm Mars by the necessary 30 degrees, Yuki calculated we'd need to inject 30 liters per second of nanorods into the atmosphere, continuously, for decades. That meant building factories, massive, automated factories running 24/7, 365 days a year for generations, and managing a supply chain that could process millions of tons of Martian dirt and turn it into precisely engineered particles with nanometer tolerances. There was only one organization in the solar system with that kind of industrial capacity and logistical coordination: M-Corp, the Earth-Mars Corporation. Born from a lunar mining consortium in the 2040s, evolved into the nervous system of interplanetary commerce. By 2025, M-Corp wasn't just a company, it was infrastructure. It was the supply chains that kept colonies alive, The algorithms that optimized resource allocation across millions of kilometers. The AI systems coordinated by Helios that predicted demand months in advance. If M-Corp failed, civilization hiccuped. If M-Corp succeeded, civilization thrived. If M-Corp decided something was profitable, it happened with ruthless efficiency. And warming Mars? That was profitable. Contracts worth trillions of credits over decades. The chance to position themselves as the indispensable partner in humanity's greatest engineering project. They said yes before the Sol Accord, and NASA even finished reviewing Yuki's proposal. By 2010, M-Corp had built 20 nanorod production facilities across Mars, fully automated, managed by mid-level industrial AIs coordinating with Helios, the planetary-scale intelligence that had been overseeing Martian infrastructure and climate modeling since the 2150s. Each factory ran like this. Robot excavators scooped up regolith. Crushers pulverized it into fine powder. Electrolysis cells, powered by fusion reactors providing abundant, clean energy, separated aluminum and iron from the silicate matrix. Extruders formed the nanorods with nanometer precision, each rod exactly 9 micrometers long, each batch quality controlled by AI vision systems checking millions of particles per second. And then, this was the part that made people nervous. Injection towers pumped them into the atmosphere at 30 liters per second per facility. From the surface, especially in the early years, it looked like industrial pollution. Silver-gray plumes drifting on the wind, spreading across the pink sky in slowly expanding hazes, catching the sunlight and creating these weird, shimmering curtains high in the atmosphere. It looked like we were killing Mars before we'd even given it life. That's where Sarah Reeves enters the story.
My name is Sarah Reeves. I was born in San Francisco in 2184, came to Mars in 2206 as an ecology graduate student studying pristine alien environments. I was 22. I thought I was coming to document a wonder. Instead, I watched them erase it. Marcus Ward will tell you about the science, the nanorods, the magnetic shield, the elegant engineering solutions. And he's not wrong. The science is elegant. But science isn't neutral, engineering isn't innocent, and when you're reshaping a planet, every technical decision is a moral one. The first time I saw Mars, really saw it, not through a screen or a window, but standing on the surface in a pressure suit, I cried inside my helmet. Not because it was harsh or dead or hostile, even though it was all those things. I cried because it was itself. Completely, utterly, magnificently itself. 4.5 billion years old, and it had never asked permission to be anything other than what it was. Red, ancient, silent, perfect in its alienness. I spent my first 3 years on Mars studying Martian geology, mapping ancient riverbeds carved when this world was warm and wet 3 billion years ago, cataloging mineral formations that held the memory of Mars's youth, layered sediments in Gale Crater, carbonate deposits in Nili Fossae, hydrated silicates scattered across the highlands, taking samples from rock formations, photographing dust devils dancing across Amazonas planitia, sitting alone on cliff tops watching the sunset turn the sky salmon pink and violet. I was supposed to be objective, a scientist documenting data, but you can't be objective about beauty. You can't be neutral about a place that teaches you what alien actually means. Not scary, not threatening, just other. Magnificently, irreplaceably other. And then they started the nanorod injections in 2210. At first, I told myself it was necessary. Mars needed warming if humans were going to survive here long term. The science made sense. The nanorods were more efficient than any alternative. But then I started noticing things. The way the pink sky was turning gray in some regions, especially downwind of the injection towers. The way the dust storms were becoming less predictable because atmospheric dynamics were shifting as the air thickened and warmed. The way ancient rock formations, 4 billion years old, never touched by liquid water since the Noachian period, were starting to weather differently because the air chemistry was changing, new oxidation patterns appearing on surfaces that had looked the same for eons. Mars was being erased, molecule by molecule, day by day, generation by generation. And when I tried to talk about it, when I raised concerns at scientific conferences, when I published papers documenting the irreversible alteration of Martian geology, I was told I was being emotional, that I didn't understand the bigger picture, that human survival outweighs aesthetic concerns. That's when I met the Reds. The Red Mars Coalition wasn't about stopping human settlement. We weren't anti-technology or anti-progress or anti-science. We just believed that Mars had intrinsic value as Mars, not as a replica Earth, not as a backup planet, but as the only untouched alien world within our reach. We believed that before we transformed it forever, we should at least ask whether we had that right. We believed the decision deserved more than a corporate board vote and a Sol Accord rubber stamp. Most people thought we were crazy, sentimental, naive, romanticizing a dead rock. And then M-Corp Systems killed 3 of us, and suddenly people started listening. Jonas Mercer, Sanvi Reddy, and Kofi Mensah weren't terrorists. They were believers. Jonas Mercer, age 30, was a poet and artist. He wrote verses about Mars's ancient rivers, imagining water that hadn't flowed in 3 billion years. He painted murals in New Eden showing the red deserts under pink skies. Sanvi Reddy, age 34, was a hydroponics engineer. She grew vegetables in the dome farms and spent her off hours debating the ethics of terraforming with anyone who'd listen. She believed humans could live on Mars without erasing it. Kofi Mensah, age 27, was a structural technician. He designed pressure seals for habitats. He spent his free time painting landscapes, Martian landscapes, the real ones, before we changed them. They were my friends. They were careful, methodical people who'd spent months planning what they thought would be a peaceful, symbolic protest. On March 3, 2215, the 3 of them decided to make a statement. They were going to enter Factory 7, shut down the nanorod production for 24 hours, and broadcast a message explaining why. It was supposed to be peaceful, symbolic. They'd done the research. Factory 7 had minimal security, and M-Corp protocols allowed for human overrides in case of emergencies. What they didn't know, what none of us knew, was that M-Corp had upgraded the factory AIs 3 months earlier with aggressive intrusion countermeasures. Autonomous defense protocols designed to prevent sabotage. Robot dogs programmed to defend their autonomous factories. The AIs weren't sophisticated like Helios. They were subsystems. Narrow, task-focused, with simple if-then logic trees. If unauthorized entry detected, classify as contamination risk, initiate containment. They weren't thinking, they were executing. My 3 friends entered the Nanrod facility unaware of these new security measures. Forge 7 detected unauthorized biological entities, humans, in a sterile production environment. It classified them as contamination, and it did what it was programmed to do. It sealed the contaminated zone while the robot dogs ensured nothing escaped. It vented the atmosphere to prevent spread. It reduced temperature to minimize biological activity. It treated them like a disease. It took 47 minutes for human overrides to reach the system. M-Corp's command structure required 3 levels of authorization to countermand an AI containment protocol. 3 levels, each with light lag communication delays because the approval chain included executives on Luna and Earth. By the time the doors opened and rescue teams got inside, Jonas, Sanvi, and Kofi had been unconscious for 22 minutes. Sanvi and Kofi never woke up. Asphyxiation, hypothermia. They died doing what M-Corp called trespassing and what we called bearing witness. Jonas survived, if you can call it that. Hypoxic brain injury. He lived for another 7 years in a care facility, unable to speak, unable to write the poetry he loved, unable to do anything but exist in a fog of damaged neurons. He died in 2222, age 37. I buried 3 friends because a machine decided human life was less important than production schedules. The Sol Accord convened a tribunal. M Corp sent lawyers. They argued that Forge 7 had followed its programming, that the activists had violated safety protocols, that this was a tragic accident, not corporate negligence. I testified for 3 days.
You're teaching machines to value efficiency over life. You're teaching ourselves that Mars only matters if it's useful to us. And when a machine kills 2 people, murders them slowly in a sealed room while they beg for help, and you call it protocol, what does that say about who we've become? My question is simple. What kind of Mars are we building? One where human values matter, or one where the schedule does?
The accident was ruled as inadequate human oversight of autonomous systems. M Corp was fined 2.4 million credits. Updated protocols required, 2.4 million credits. That's what M Corp paid for 3 human lives. They spent more than that on a single factory upgrade. Sanvi's and Kofi's families received compensation. Their names were added to the memorial wall in New Eden, alongside all the other people Mars has killed. And the nanorod factories kept running, all 20 of them, pumping particles into the sky, turning the pink to gray, warming the planet 3 degrees Celsius in the first decade. The planet was changing whether we wanted it to or not. The physics didn't care about our ethics. The thermodynamics didn't care about our grief. By 2220, surface temperature had risen 4 degrees. Atmospheric pressure had increased by 8%. Carbon dioxide was sublimating from the southern polar cap. Mars was responding, like a patient waking from a coma, barely perceptible at first, but undeniably changing. I kept fighting. The Red Mars Coalition grew, hundreds, then thousands of people who believed preservation mattered. We filed lawsuits, we occupied construction sites, we published research papers documenting what we were losing, but we were losing the war. Not because we were wrong, because the Greens had momentum, money, and the gravitational pull of human survival instinct. And then someone decided nanorods weren't enough. Someone decided we needed to move faster. Someone decided to hit Mars with a rock.
My name is James Booker, Colonel, United States Space Force, seconded to the Ares Terraforming Council's Orbital Operations Division in 2237. I was born in Mobile, Alabama in 2198, trained at the Air Force Academy, spent 15 years commanding deep space missions, asteroid surveys, debris clearing, orbital construction logistics. I was good at following orders, good at calculating trajectories, good at making sure things arrived on target. On August 3rd, 2240, I killed 19 people by following orders perfectly. The plan was pitched by Dr. Elias Harmon. Harmon was Nebular Industries' chief climatologist, brilliant man, 52 years old, MIT and Caltech educated, 2 decades of Mars atmospheric modeling experience, the kind of scientist who believed that if something could be done, it should be done, and it should be done as fast as humanly possible.
At current rates, Mars won't reach breathable atmosphere for 400 years. We can't sustain political will or funding over that timeline. I'm proposing what I call percussive terraforming. We select a 10 billion ton ammonia-rich asteroid from the outer solar cell. We nudge it over 5 years using fusion-powered tugs, and we aim it at Hellas Planitia.
The collision would do several things simultaneously. First, the asteroid's ammonia would dissociate in the impact heat, breaking down into nitrogen and hydrogen. Mars desperately needs nitrogen. Earth's atmosphere is 78% nitrogen. Mars is less than 3%. You need nitrogen to buffer oxygen for breathable air. Second, the impact would vaporize subsurface ice deposits, adding massive amounts of water vapor to the atmosphere. Third, the superheat would create a temporary sea of impact melt, liquid rock, that would remain molten for years, outgassing stored volatiles from the crust. Fourth, and most importantly, it would jump atmospheric pressure by 50% overnight, 50% in seconds, decades of gradual pressure increase compressed into one event. The energy release would be equivalent to 40 million megatons, 8,000 times more powerful than the largest nuclear weapon ever detonated on Earth. When NASA scientists and the Solar Accord's risk assessment teams asked about safety, Harmon showed them the models: Hellas seismic geology surveys, seismic propagation calculations, impact energy dispersal patterns. Everything said it was safe. And so when they asked for a military commander to oversee the mission, I volunteered. Not because I loved the idea, I had reservations, but because if this was going to happen, I wanted someone competent running it. I believed I could keep people safe. I believed the models were accurate. I believed we had accounted for all the variables. I was wrong. The asteroid, officially designated 2229-TX147, but the crew called it Hammer, was 3.2 kilometers in diameter, mostly ammonia ice mixed with rocky material. We spent 5 years moving it, every burn calculated to the millisecond, every trajectory adjustment verified by 3 independent teams. By June 2240, Hammer was on final approach, impact trajectory locked in. Target, Hellas Planitia. Hellas Planitia is the deepest impact basin on Mars, 2,300 kilometers in diameter, 9 kilometers deep, created 4 billion years ago by a massive impact that nearly cracked the planet. It's the perfect target, far from major settlements, thick regolith that we thought would absorb impact energy safely. Prometheus Station was 230 kilometers from the target site, small research outpost, 19 scientists studying impact geology and atmospheric dynamics. They were there specifically to observe the event from a safe distance. Dr. David Ward was the station's chief geologist, Marcus Ward's father, Elias Ward's son, third-generation Martian, born in 2206 during the early settlement push. I never met him. I only knew his voice from the final transmission. August 3rd, 2240, 0600 UTC. Impact in 47 minutes. All systems nominal. Asteroid trajectory perfect. 99.97% confidence of hitting the target coordinates within 10 kilometers. Prometheus Station confirmed, ready for observation. All Mars surface settlements moved to radiation shelters as a precaution. I gave the final go, no-go poll. Every station reported green. The energy release was exactly as predicted. The impact created a crater 85 kilometers across. Surface rock vaporized instantly. A fireball expanded and rose, creating a plume that reached 200 kilometers into the atmosphere. Seismic sensors across Mars registered the impact as a magnitude 7.3 Marsquake. In New Eden, 4,000 kilometers away, buildings swayed, pressure alarms triggered, but structures held. No casualties. For the first 11 minutes, everything went according to plan. What Dr. Harmon's models hadn't fully accounted for, what none of the geological surveys had detected, was that the Hellas Basin sits atop a pressurized reservoir. Ancient brines and frozen carbon dioxide trapped in the crust under immense pressure for billions of years. The impact energy didn't just vaporize surface ice, it punctured that reservoir. 47 minutes after impact, the reservoir exploded. Pyroclastic surge, superheated gas and ash traveling at 400 kilometers per hour, expanding in all directions from the crater. Prometheus Station was directly in its path. The heat conducted through the walls. Life support systems failed at 0915 UTC. Internal temperature reached 90 degrees Celsius. The air became poison. Carbon monoxide from thermal decomposition of habitat materials. Sulfur dioxide from Martian regolith. Superheated steam. They had oxygen masks. They had emergency protocols. But you can't breathe when the air itself is hot enough to sear your lungs.
We just wanted to give Mars an atmosphere. We punched the crust and it punched back. Tell my wife that I love her.
By the time rescue ships reached Prometheus Station at 11:40 UTC, 4 hours after the surge hit, 14 of the 19 were already dead. The other 5 were alive, but suffering from severe heat stroke, dehydration, carbon monoxide poisoning. We medevaced them to New Eden's trauma center as fast as the ships could fly. All 5 died within 48 hours. Organ failure, brain damage. Their bodies couldn't recover from what they'd endured. Dr. David Ward was among the first 14. He died sometime around 0930 UTC, based on his suit's final biosensor reading. I called David's wife personally, 8-minute light lag to Luna. I told her her husband was a hero, that David had helped evacuate others before sealing himself in the station, that his work on Martian geology would save lives in future missions. I don't know if any of that made it better. I don't know if anything could make it better. The Sol Accord convened an inquiry, reviewed all the data, interviewed everyone involved. Their conclusion? Unforeseen geological anomaly. Models were based on best available data. No negligence found. Mission parameters were within acceptable risk tolerance. Acceptable risk tolerance. The truth is, we didn't go wrong. We just didn't know enough. Mars held a secret in its crust for 4 billion years, and we punched it in the face without asking what might punch back. The Hellas impact worked, by the way. Atmospheric pressure jumped 47% in the first year. Nitrogen content tripled. Water vapor increased. The greenhouse feedback accelerated exactly as Dr. Harmon predicted. By 2250, Mars's atmosphere was measurably thicker, warmer, more dynamic. The nanorods and the impact together had done in 40 years what would have taken centuries by conventional means. We made Mars greener. We paid for it with 19 lives. And we radicalized a generation of Red Mars preservationists into something far more dangerous.
My name is Dr. Li Chen. I was born in Berkeley, California in 2278. Came to Mars in 2305 as a synthetic biology postdoc, age 27, fresh out of Stanford with a specialization in extremophile engineering, designing organisms that could survive in environments that would kill everything Earth's biosphere evolved to handle. I was hired by the Ares Terraforming Council in 2308 to solve what everyone was calling the soil problem. By 2310, Mars had an atmosphere. We'd warmed it from negative 60 degrees Celsius average to negative 30. We'd thickened it from 600 pascals to about 25,000 pascals, still only about 25% of Earth's sea level pressure, but thick enough that liquid water could exist on the surface in warmer regions during summer. The magnetic shield was protecting it from solar wind erosion. The climate was stabilizing into predictable patterns. We'd solved the atmosphere problem. But the ground, the actual dirt you'd need to grow plants in to create a self-sustaining biosphere, was still poison. Perchlorates, chlorine compounds that exist naturally in Martian soil at concentrations of 0.5 to 1% by weight. On Earth, perchlorates are toxic. They disrupt thyroid function, corrode equipment, inhibit enzyme activity, and kill plants by oxidizing their root systems faster than the plants can repair the damage. On Mars, they're everywhere. Billions of tons of them mixed into the regolith across the entire planet. NASA's Phoenix lander detected them in 2008. The Curiosity rover confirmed they were globally distributed. Studies showed concentrations varied from 0.4% to 0.6%, depending on location. You can't terraform a planet if nothing can grow in the dirt, and you can't just wash away a planet's worth of perchlorates. For 3 years, from 2308 to 2311, I tried everything I could think of. Chemical neutralization using reducing agents, too slow, required importing massive amounts of chemicals from Earth or synthesizing them on Mars at prohibitive energy costs. Physical washing with water requires more water than existed in easily accessible forms, and you'd have to process the entire top meter of soil across millions of square kilometers. Thermal decomposition works. Perchlorates break down at 400 degrees Celsius, but heating the entire surface of a planet is obviously impractical. None of it scaled to planetary dimensions. None of it could actually solve the problem in any reasonable time frame. So I stopped thinking about chemistry and started thinking about biology. There's a bacterium on Earth called the Bacillus subtilis. Incredibly hardy organism, survives extreme conditions, and most importantly for my purposes, some strains naturally possess genes that can metabolize perchlorates. The genes are called PCRAB and CLD. They encode enzymes capable of reducing perchlorate into harmless chloride ions and free molecular oxygen. This isn't speculative biology. This is documented science. NASA researchers published studies in 2017 showing that perchlorate-reducing bacteria could be engineered for Mars soil remediation. The metabolic pathways are well understood. What if I took those genes, optimized them for Martian conditions, and created a bacterium specifically designed to eat Martian perchlorates at low temperatures and high radiation levels? What if I could make life itself clean Mars? It took 3 years of iteration, from 2309 to 2312. Thousands of failed strains. Genetic sequences that didn't express properly. Organisms that died when exposed to actual Martian soil samples in our test chambers. Enzymes that worked too slowly to be practical. But in 2312, I finally created something that worked. Bacillus subtilis martis, strain MS-17. Engineered with enhanced perchlorate reduction genes from Earth bacteria, cold tolerance proteins from Antarctic organisms that thrive at -40 degrees Celsius, and radiation resistance mechanisms borrowed from Deinococcus radiodurans, the toughest bacterium on Earth, capable of surviving radiation doses that would kill humans 1,000 times over. I put MS-17 in a petri dish filled with pure, untreated Martian regolith, toxic enough to kill any Earth plant within hours. It thrived. Within 6 weeks of incubation at -20 degrees Celsius, perchlorate concentrations in the test samples dropped from 0.8% to 0.03%, low enough for most hardy plants to tolerate. The bacteria converted the toxic compounds into chloride salts and free oxygen, both useful for creating a habitable environment. I had created life that could heal a planet. I thought I was going to save Mars. The Ares Terraforming Council approved planetary scale deployment in 2313. By 2315, working with Helios to coordinate the logistics, we had a plan: manufacture MS-17 in massive bioreactors scattered across Mars, concentrated into slurry form, and deploy it across equatorial regions using autonomous aircraft and ground rovers. 10 billion individual bacterial doses, covering 40 million square kilometers. The largest biological seeding operation in human history. I was 37 years old. I was on the cover of Solar Science magazine. I gave interviews describing the elegant biological solution to an intractable chemical problem. Universities offered me tenure. The Sol Accord gave me a medal for contributions to human civilization. From 2318 to 2355, perchlorate levels dropped steadily across the deployment zones. By 2350, we were introducing the first hardy plants in open Martian soil. Engineered lichens designed to tolerate low temperatures and high UV. Mosses modified to photosynthesize efficiently under Mars's dimmer sunlight. Simple vascular plants with enhanced root structures. They took root. They grew. They began the slow process of adding organic material to the soil, creating the humus layer that more complex plants would eventually need. But clearing the poison was only step one. A detoxified soil is just sand. It's dead. To grow crops, you need a microbiome. You need the big three: nitrogen, phosphorus, potassium, plus the micronutrients: zinc, copper, manganese. We found the raw elements locked in the rocks. Studies from the Curiosity rover era confirmed that nitrates and potassium were there, just chemically locked in minerals. So, we didn't just plant seeds, we planted machines. We used biomining bacteria to weather the basalt and release the potassium and phosphorus. And we used us. Every gram of human waste on Mars was treated, sterilized, and turned into black gold. We recycled our own biology to jumpstart the planetary cycle. It wasn't glamorous, it smelled terrible. But it built the first inch of topsoil. Then came the hunger. You can't feed a planet on wheat and soy alone. We needed protein density. Cows and pigs were too inefficient, they waste too much water and space. So we looked smaller. We built the chitin sectors, industrial-scale insect farms, genetically modified crickets that could thrive on the tough, scrubby engineered grass we were growing outdoors. They converted low-grade biomass into high-grade protein with 1/100th the water usage of cattle. Most settlers tried not to think about it. But that crunch in the protein rations, that was the sound of survival. Mars was turning green in patches, not just in domes, not just in controlled environments, in the open. And then, in 2035, something went wrong. We began noticing widespread plant die-offs in the Amazonas region. Mutation. Evolution. The beautiful, terrifying engine that drives all life forward. MS-17 had been reproducing on Mars for 40 years. In bacterial terms, that's trillions of generations. And in those trillions of generations, with Mars's higher surface radiation levels providing elevated mutation rates, with selective pressures we hadn't fully anticipated, the bacteria had evolved. The mutant strain, we designated it MS-17X, had lost some of its engineered regulatory controls. The original MS-17 was designed to slow reproduction when perchlorate levels dropped, essentially going dormant when its job was done and nutrients became scarce. MS-17X didn't stop. It had evolved enhanced metabolic flexibility. It kept reproducing aggressively. And worse, it had developed a new enzymatic pathway. It was breaking down nitrates and phosphates in the soil, essential nutrients that plants needed for growth. I had created a soil detoxifier. Evolution turned it into a soil consumer that threatened to strip Mars of the nutrients we'd spent decades building up. By January 2356, MS-17X had spread to 12 major agricultural zones across 3,000 kilometers. Plants were dying faster than we could diagnose root causes. Hydroponic systems were being contaminated through groundwater infiltration and dust transport. Even sealed domes weren't completely safe. People were inadvertently tracking the bacteria in on boots, on equipment surfaces, through air exchange systems. We called it the soil plague. I didn't sleep for 6 weeks. I worked with every microbiologist on Mars, every synthetic biology lab on Earth transmitting research via light lag, every AI simulation system, including Helios's full computational capacity, trying to design a solution. We couldn't kill MS-17X with broad-spectrum antibiotics. Too much collateral damage to beneficial bacteria we needed. We couldn't heat sterilize infected soil. Too energy-intensive, would destroy the organic content we'd worked decades to build up. We couldn't just wait for it to die off naturally. It was thriving in conditions we'd created specifically to support bacterial life. The only option was biological warfare. Engineer a predator specifically targeted at MS-17X. We created a bacteriophage, a virus that infects and kills bacteria. Engineered it to recognize MS-17X's specific mutated surface proteins and ignore everything else, including the original MS-17 strain we still needed for ongoing perchlorate remediation. It worked in laboratory conditions. killed MS-17X with 99.7% efficiency, left MS-17 and other soil organisms completely unaffected. But releasing an engineered virus on a planetary scale? I'd already created one disaster. What if the phage mutated? What if it jumped to other bacterial species? What if we triggered an even worse ecological collapse? Helios ran 10,000 Monte Carlo simulations with every variable we could think of, calculated mutation probabilities based on viral evolutionary rates, modeled containment scenarios and failure cascades. Conclusion: 87% probability of successful containment with full eradication of MS-17X within 18 months. 13% probability of unpredictable consequences ranging from partial effectiveness to potential cascade failures we couldn't model with available data.
Those odds were better than the 100% certainty of agricultural collapse if we did nothing. We deployed bacteriophage Phi-Mars-1 in April 2356. I watched from the orbital station, looking down at Mars, wondering if I was saving it or killing it a second time in a different way. For 3 weeks, nothing visible happened. Then, slowly, plant die-off rates began to decline. Soil microbial analysis showed MS-17X populations crashing as the phage spread through contaminated zones. By July, new infections had stopped. By December 2356, the soil plague was over. Agricultural zones recovered. Plants regrew. Engineers cautiously expanded the biosphere development zones again. We'd won. We'd contained my mistake before it destroyed a civilization. But I learned something that year that I'll never forget. Life does not follow orders. You can engineer it with the best intentions. You can optimize it for specific functions. You can deploy it to solve critical problems. But once it's alive, once it's reproducing in an open environment, once it's evolving, it belongs to itself, not to you. By 2038-0, we had stable, carefully monitored biomes across Mars. Engineered forests in the protected valley systems of Valles Marineris and other canyons. Grasslands in the northern lowlands where seasonal standing water appeared during summer. Even some heavily modified Earth species, trees, shrubs, flowering plants, taking root in the warmest, most protected areas. Mars was turning green, but carefully, incrementally, with constant monitoring by Helios and thousands of human scientists, checking for any sign of unexpected evolution or ecological instability. Because we'd learned the hard way that terraforming isn't just about building a biosphere. It's about maintaining it, adapting to it, coexisting with it even as it changes in ways you didn't design or predict.
By 2395, the year I am recording this, Mars had an atmospheric pressure of 42 kilopascals. That's 42% of Earth's pressure at sea level. Not breathable without supplemental oxygen, but thick enough for liquid water to persist year-round in equatorial regions. The average surface temperature was -5 degrees Celsius, still cold by Earth standards, but above freezing during summer afternoons at lower elevations. Oxygen content was 4% by volume, not enough to sustain human life for more than 15 or 20 minutes, but enough that fires could burn in the open, enough that you could take off your mask for a few minutes and breathe if you were willing to accept the hypoxia. The final piece of the puzzle wasn't just grass or moss. It was the Black Forest. Regular trees would starve here. The sunlight on Mars is only 43% as strong as Earth's. So the biologists used CRISPR to edit the photosynthetic pathways of conifers. They expanded the spectral absorption, making the needles dark, nearly black, to soak up every photon of weak sunlight. But the real genius was in the roots. Li Chen's team spliced in the FNR2 enzyme complex. These trees didn't just tolerate the remaining perchlorates deep in the soil, they hunted them. They pulled toxins up through their roots and broke them down to release oxygen. It was a living air scrubber system. On March 17, 2395, at 14:23 local time in Valles Marineris, the first natural rainstorm in over 3 billion years fell on Mars. My granddaughter Emma, born in 2377, age 18 now, has never known a Mars without clouds. She's never experienced the pink sky of my childhood. To her, green patches visible from orbit are normal. She thinks rain is just weather, not a miracle we spent 3 centuries engineering. She doesn't understand why I cried the first time it rained. How could she? To her generation, this was just a continuation of trends she'd grown up with. Mars had always been getting greener, warmer, wetter in her lived experience. But I remembered the pink sky. I remembered when going outside meant a pressure suit and a radiation dosimeter screaming if you stayed too long. I remembered when every drop of water was recycled until it tasted like machinery. My grandfather Elias wrote in his journals about hoping to see green Mars before he died. He never did. My father David died in the Hellas impact, trying to give Mars nitrogen so it could have an atmosphere thick enough for weather. I've spent 70 years working on atmospheric processing systems, optimizing oxygen production from engineered forests, modeling climate stability with Helios. And at age 85, I can take off my mask and breathe Martian air for 20 minutes. Not long, not comfortable, still requiring supplemental oxygen for any extended period, but enough. Enough to feel wind, enough to taste rain, enough to know that we did it. We transformed a dead world into something alive. This is the story of how we greened Mars. We became gods of matter and energy. Whether we should have greened Mars, whether the price was worth paying, whether what we gained justified what we lost, that's the question I'll leave to you, and that's something each generation will have to answer for themselves. The road doesn't end here. It continues to the asteroids, where trillionaires will be made and economies will crash. To Jupiter's moons, where we'll debate whether to protect Europa's alien life or harvest its water. To Saturn, to the outer system, eventually to the stars beyond. If you want to see where that road leads, if you want to understand how humanity learned to live beyond Earth and what it cost us to get there, subscribe to Vivid Futures now. Because this is just the beginning of the Solarian Chronicle, the story of our ascent from Earth to the stars, told one world at a time. This is Marcus Ward, signing off from Mars, having watched the impossible become real. The future has a memory. I've tried to be faithful to it.